Hello, in this video, I'm going to stress for you the difference between the mass of something and the number of that thing you have. This is a really important conceptual step to understanding this unit and the next one after. Let me review some old stuff you need to know. We learned about the mole, and 1 mole of something is 602 billion trillion copies of that thing. We normally write the number 602 billion trillion as 6.02 times 10 to the 23rd power. In fact, in chemistry, whenever we're dealing with a very, very big number, we normally write it as a small number multiplied by 10 to a large power because it makes it much easier to write and think about. We also learned that the molar mass of something is just the mass of 602 billion trillion copies of that thing, so it's the mass of 1 mole. The molar mass is something you could theoretically figure out for anything. So there's a molar mass for apples, and there's a molar mass for bricks and elephants. But the molar mass for most things is way too big to be useful. The only kinds of things the mole and the molar mass are useful for are atoms and molecules because they're so small that you need to deal with very large groups of them for them to actually be noticeable in your life. And we also learned that every different atom has a different mass, and therefore they all have different molar masses. You can find the molar mass in grams on the bottom of a periodic table box because chemists have already figured out how heavy these things are. So for example, I have 2 periodic table boxes right here, one for oxygen and one for uranium. If you had 602 billion trillion oxygen atoms, which is 1 mole of oxygen, they would weigh 15.999 grams, so about 16 grams together. And if you had 1 mole of uranium atoms, which is 602 billion trillion atoms, they would weigh about 238.03 grams. This should say 3 and not 2, sorry. Now, if you have 1 mole of oxygen and 1 mole of uranium, you have the same number of atoms in a mole of each. But the uranium is heavier than the oxygen. So imagine that this is not the number 4, it's 602 billion trillion. The number isn't very important. You can have the same number of both, but have uranium be heavier than the oxygen is. This is why uranium has a higher molar mass. It's not because 1 mole of uranium is more atoms. 1 mole is always the same number of atoms. But even though you have the same number of atoms, every single uranium is heavier than a single oxygen. So that's why the molar mass ends up higher. Now let's get to the new stuff in the math, mole conversions. So pretend like you're in a desert and you're thirsty because you have no water at all. What you do have for some reason are containers of pure oxygen and hydrogen because you brought your chemistry truck, I guess. So oxygen and hydrogen in containers. Now in reality, the oxygen would be O2 and the hydrogen would be H2 because these are diatomic elements, which means they're unstable when they're alone. But let's pretend like they're just single oxygen and hydrogen atoms to make this easier. So you have a box full of only oxygen atoms and a box full of only hydrogen atoms. Now you know that you can make H2O by adding 2 hydrogens to 1 oxygen, right? 2 hydrogens and 1 oxygen will give you 1 water molecule, which is H2O. So you can get water to drink by mixing 2 hydrogens with 1 oxygen. So you get a cup, and you add 2 grams of hydrogen, because you can't count molecules, right? But you can take a scoop and scoop in 2 grams of hydrogen and 1 gram of oxygen, and you can mix it so that it reacts, and you get something. Then you drink it, because you think you just made water, right? You added 2 grams of hydrogen, 1 gram of oxygen, so you must be making water. And you drink it, and you die, because you didn't make water, you made acid instead. This is what would happen if you mix together in this ratio. So what happened? Why did you make acid instead of water? What went wrong? This is where you messed up. This reaction tells you the number of atoms that you need. You need 2 hydrogen atoms and 1 oxygen atom to make 1 water molecule. So the reaction is about the number of things you need. Atoms are too small to count, so you couldn't tell what number of oxygen and hydrogen atoms you added. You didn't use tweezers and count them out. Instead, you added 2 grams of hydrogen and 1 gram of oxygen, because you could measure a gram out if you couldn't measure an individual atom. And you just assumed that 2 grams of hydrogen and 1 gram of oxygen would also work out, because there's a 2 there and there's a 1 there. But the numbers in this chemical reaction do not tell you the mass or the weight. They're not related to the mass or the weight of the chemicals. You added 2 grams of hydrogen and 1 gram of oxygen. But hydrogen and oxygen, they have different masses. When you added 2 grams of hydrogen, you added about 2 moles of hydrogen. Because hydrogen, the molar mass is about 1, right? So 1 mole of hydrogen is about 1 gram. So 2 grams is like twice that much, 2 moles. So you added 2 moles of hydrogen, which is 2 times 1 mole of hydrogen atoms. And remember, we write 602 billion trillion like this. So if you just do the math, you can figure out how many hydrogen atoms you added. It was about this many hydrogen atoms. 1.204 times 10 to the 24th power. That's a lot. And when you added 1 gram of oxygen, you added about 1/16 of a mole of oxygen, right? Because oxygen is about 16 grams per mole. So if you added 1 gram, that's 1/16 of 16th grams. So that's about 1/16 of a mole. That's about how much you added. And that is 1/16 of 1 mole of oxygen atoms. So you added about 3.763 times 10 to the 22 oxygen atoms. Now, you added this much hydrogen and this much oxygen, and if you actually try to pair up 2 hydrogens for every single oxygen, you're going to end up with a lot of leftover hydrogen. A lot of leftover hydrogen. In fact, this is about how many leftover hydrogen atoms you'll have. 5.6 times 10 to the 23, which is 560 billion trillion leftover hydrogen atoms. Now, extra hydrogens will take your H2O, which is water, and it will turn it into H3O, which is hydroxide. They look very similar, but hydroxide is actually a very strong acid that will kill you very painfully. So, what was the lesson here? Sometimes a chemical recipe will tell you the number of atoms or molecules to add. But the number of atoms or molecules does not tell you anything about the mass to add. The 2 and the 1, they tell you the number of hydrogens and oxygens to add. But that does not tell you how much mass or weight. This does not mean that you can add 2 grams of hydrogen to 1 gram of oxygen, or 2 pounds of hydrogen to 1 pound of oxygen. This tells you nothing at all about the mass that you need to add. Only about the number. Mass is not the same as number. As an example, to make it maybe more intuitive for you, which one has more things in it? A 4-pound box of apples or a 36,000-pound box of elephants? You know, are there more apples in this box or elephants in that box? And you might be tempted to say, well, this is so heavy, right? So there must be more elephants in this box than there are apples in that box. But that's not true. Because if you actually look at it, you can have 4 pounds of apples. That's about 12 apples. And 3,600 pounds of elephants is about 6 elephants. So this is like a dozen apples and like a half dozen elephants. So you can maybe tell that you have more apples even though it weighs less. This weighs more, but every elephant is heavier, so you have fewer things here. This is kind of the metaphor that I want you to think of. Let's bring it to chemistry and try to make it relevant. Why am I teaching this to you? Well, in the real world, it is absolutely impossible to count atoms. They are way too small. 1 single pixel of your screen has billions of atoms in it. You cannot figure out where an atom is or move them in groups. But we can weigh chemicals on a scale. So we can take a scale, scoop in some powder, and figure out the weight of that powder. And this is how chemists actually deal with chemicals, by weight or mass. And if we know the weight, we can calculate the number of atoms using the molar mass. So we can figure out how many atoms are in this cup right here by using the weight and the molar mass of the chemical. The molar mass relates a number to a mass. Specifically, it relates this number to a mass. It tells you what mass 602 billion trillion copies of a chemical are. So we're basically going to be abandoning the idea of a single atom, and we will be talking about groups of atoms. Groups this big called moles. So mole is what we're going to use to figure out number. I'll show you 2 examples. First, how we can use the molar mass to figure out the number of atoms if we know a weight. So let's say that I use a scale and I measure out 28 grams of nitrogen. How many atoms of nitrogen is that? How could I possibly figure that out? Well, I can't figure it out right here. I have to know how heavy a group of nitrogen is. And the weight of a nitrogen atom is recorded in the molar mass of nitrogen on the bottom of the periodic table box. So the molar mass of nitrogen is about 14 grams. I'm going to round off this 0.07 because that makes this easy. And that means that 28 grams is about 2 moles, right? Because 1 mole is about 14. 28 is 2 times as big as 14. So I must have 2 moles, not just 1 mole. So 28 grams of nitrogen is 2 moles of nitrogen, and I know that a mole is just 602 billion trillion atoms, right? So 2 moles of nitrogen is 2 times this number of atoms. So 2 moles of nitrogen is 2 times 602 billion trillion, or 6.02 times 10 to the 23rd. And you could just put it in a calculator. It gives you 1.204 times 10 to the 24th atoms. That's what 2 moles is. And so, that's the answer. Ta-da! I figured out the weight of nitrogen on a scale. I figured out how many moles that was using the molar mass. And then I figured out how many atoms that was using the fact that 1 mole is 602 billion trillion atoms. So we can also use the molar mass to figure out the weight of a number of atoms. So we can go the other way. For example, let's say that I have 4.56 times 10 to the 22 atoms of iron. Or really, I know that I need this much iron, maybe for creating some kind of medicine. Well, I know that 1 mole is 6.02 times 10 to the 23rd atoms. So I gotta know how many moles this is. It's less than 1 mole, because that's less than 10 to the 23rd. So I'm gonna divide. I take the number of atoms I have, I divide it by the number of atoms in a mole to figure out how many moles I have, and that's 0.075 moles. So this right here is 0.075 moles of iron, and then I can figure out how heavy that is by using the molar mass. I need to look at the periodic table to go from a number to a weight, but scientists have recorded that for us. So I know that 1 mole is 55.845 grams, and that means that 0.075 moles is 0.075 times a mole, which is 4.19 grams. So I can go there, figure that out. That was it. The point of this is to show you that the number of atoms and the number of moles are pretty much the same. Like the number of atoms and the number of moles are the same, because moles and atoms, they both measure number. The number of something that you have. But you can't necessarily figure out the mass from the number. For example, 0.075 moles of iron is going to be different than 0.075 moles of hydrogen or oxygen. If you want to go from a number to a mass, then you're going to have to look at the molar mass on the periodic table and do a conversion, which is what we're going to end up doing more of later. So I hope that was helpful.